Entitled Learning Monotone Nonlinear Models Using the Choquet Integral by Ali Falaterani, Weiwei Cheng, Christoph Demchinsky, and Eike Hüllermeier.
All right. So, how are you? I realized I was the guy between you and the lunch, so a lot of pressure here. It's very pleasure to be here. I just want to mention that I studied my master here in marketable, so it's always a pleasure to come back here. Today I'm going to talk about some recent research from our group on how to use Choquet integral to design monotone nonlinear models. Now this is a joint work with my colleague Ali, Christoph, and also my PhD advisor Eike Hüllermeier. So these are the photos here, in case you don't recognize the face. So everybody working in the learning then probably know that if you work in any application, it's very important to incorporate your background knowledge into the learning process. There is one specific example which we consider in this research is monotonicity. As a monotonicity is of course very important. For example, imagine you're designing a medical, predictive model for medical application. And of course, if you want to say, predict how likely a patient has cancer, then you would like to have something like, if the more the patient smoke, the more likely they got cancer, right? And if your model eventually cannot ensure this, probably a medical doctor would not like to trust the model. It probably leads to a dislike of the model and just give up your model. Of course, you don't want that to happen. Now, to ensure monotonicity for a linear model is quite obvious because the monotonicity directly corresponds to the sign of the coefficient. And linear model is also very easy to interpret because we have linear coefficient, then the direction of the strand of influence just directly corresponds to the coefficient. And maybe one drawback, maybe the only drawback of a linear model is not so flexible. So maybe some real-world application is not just powerful enough for your application to handle. And a nonlinear model, on the other hand, is more flexible. For example, here we consider a very simple nonlinear model. We have a linear part, we just simply add some interaction term into the linear model. So we have a very simple nonlinear model, which is also, by the way, very widely used in statistics. Already for this very simple nonlinear model, if you take the partial derivative, you found out that it's one partial derivative on one single attribute. It depends on all other attributes. So now in this situation, it's very difficult to pose a sufficient and necessary condition on monotonicity, right? And also, in general, that nonlinear model is much harder to interpret than a linear model. These 3 points not only hold for this single nonlinear model, but also hold in general for other nonlinear models, like for example, multilayer neural networks and decision trees and so on and so forth. Okay, so in this part, oh my gosh, this is a very nice animation like this. But I don't have so many. I only have 2, so we want to introduce Choquet integral as a key ingredient in designing monotone nonlinear models. And as a concrete example of the Choquet integral, we will extend this logistic regression model using Choquet integral, leading to which we call choquistic regression model. Okay. And first, in the forward, I will first introduce you what is a non-additive models, and then introduce what is Choquet integral. Then we talk about how can we use Choquet integral to design choquistic regression, and then we'll show you some very first experimental results. Okay, so let's first talk about additive and non-additive models. Okay, so I guess we didn't have so far I haven't seen so many mathematical equations in this morning. Now I'm going to show you some, in case you like something. Now we have a set of C, which is a finite set. For the ease of representation, let's just for now consider the C binary values, also binary categories. And we have a measure mu, which is defined on this set C. So for example, you can consider C just like a set of skills, speaking Chinese, coding Java, and coding C, for example. And we have this mu on a set A, which you can just simply think as something like the weight of the set A. So how important is this set? For additive model, which means that as long as the two sets are disjoint, then the weight of the set A union B is the same as the weight of A plus the weight of B. So here's the example. Let's say if the weight of speaking Chinese is 0.2 and the weight of coding Java is 0.4, then we have the weight of speaking Chinese and coding Java is 0.6. Fair enough. And a non-additive model, on the other hand, it is simply normalized and monotone, but not necessarily additive. So what does that mean? Imagine that you want to find a Java programmer which is located in Beijing, right? Then you probably would like to have a some kind of scoring system. For example, if this guy only speaking Chinese, only coding Java, or only coding C, is not a good candidate, right? Because it cannot do the job. And if he's speaking Chinese at the same time also coding Java, it's a perfect candidate. And if coding C and speaking Chinese is 0.7, because the Java is fairly similar to C, so this guy is probably also a pretty good candidate. But this guy knows all these three. He also have evaluation of 1 because coding Java is already sufficient enough, and speaking Chinese go together. So if coding in C in this situation doesn't bring any additive value for this candidate. So this is a non-additive model, and you can see that here, this kind of semantic you cannot represent using the additive model. Right? So this is what is a non-additive model. Now, let's give you some more insight into this different things. Now let's talk about importance of a criteria and interactions. Now for additive model, there is no say, we don't have any possibility to model this interaction between criteria because it's linear, it's additive. And the importance of one criteria CI can be simply measured by this mu CI with the singleton because it's additive. On the other hand, for a non-additive model, the things of course become much more complicated. Now, I just want to short into the two already introduced models. First is the Choquet index and the interaction index. So this Choquet index can be used to measure how important one single criteria is. I just want to give a very intuitive idea. So the basic idea is just to measure the average increase in terms of importances when I add this criteria into another subset. This is only a intuitive idea. And at the same time, we also have the interaction index, which can use to compute the interaction between two criteria, or say two features. Okay. I won't go to details here. I only want to mention that is, as long as a non-additive model is given, I can just use this to compute the value. Right, so this is all I want to say. Okay. After talk about this non-additive model, then we can introduce this what is Choquet integral. So far, we only consider this CI is a binary feature. Either it's there or not there. But in general, the evaluation of one criteria, namely FCI, can range between 0 to 1. Okay. Now the question is, if I give you the evaluation of each individual criteria, how to get the overall evaluation of the whole thing? Now, mathematically speaking, the overall evaluation is correspond to an integral. Now, how do you do integral? If you have additive model, then the integral can be computed in a normal way. So basically, it is a vertical way. You just consider each criteria one by one and weight it using their weight, right? So this corresponds to weighted mean. This is how you normally do integral. This is a vertical way. Now, when I'm speaking vertical way, then it might already occur to you, we also have a horizontal way to compute the integral. So here I give you an example. For the same thing, we can do the integral in the following way. We first ask ourselves, how many of the criteria has an evaluation at least as much as say 4? In this case, all of them. And then we ask ourselves, how many of the between the evaluation of C2 and C4? Okay. Then we weight this according to another mirror. Then so on and so on. Okay. By doing integral in this horizontal way, as you can see here, we can incorporate this non-additive model in a very natural way. Right? We just weight it is 1 by 1, which cannot be done in the left-hand side because all the criteria are considered 1 by 1 for each other. Okay. So basically, this is already the definition of a Choquet integral. I just put the formal definition here, but actually what that is just simply what I just told you. We do the integration in a horizontal way, then I can weight it using a non-analytical method. Okay, this is Choquet integral. And of course, we want to use a Choquet integral in learning. So here we propose an extension of this logistic regression model. You're probably familiar with logistic regression. So basically, what logistic regression do is it just model the postulate probability given the instant. What is the chance that the instant is a positive class? We model this probability using a logistic function. So here we have a linear combination between the weight and features. Right? And what we do here is we replace this linear part with Choquet integral and then two another model parameters. Okay? Actually, you can show that by proper parameterization, indeed, this model can be reduced to a logistic regression. So indeed, it's a proper extension of the logistic regression model. Now, to better understand the model, I'll just give you an intuition behind it. So you can integrate this choquistic regression as a two-stage process. So first of all, you evaluate your instant. So you have a utility using the Choquet integral. And then in the second step, you make a discrete choice using this utility and compare it with a threshold beta. Okay? And we have another parameter, which is the gamma. So here we have an illustration to show you what the different gamma influence more model. So if you have a very large gamma, so let's say the gamma go to infinity, then the decision function is a step function. So which means as long as my utility is more than the threshold, then the chance this instance positive is 1. And if you choose a smaller gamma, then this decision function becomes a smooth function. So which means that even though the utility probably is more than threshold, but there's still a chance that this instance is not positive. And of course, it's also possible because probably that your utility function didn't reflect your underlying data so well, or maybe the feature you have doesn't reflect the nature of the problem so well. Of course, in that sense, this gamma can be interpreted as a position of the model, how correct the model is. Okay. So let's just give a short summary here. That we have some features of the choquistic regression model. That we have this non-linear matter mu, which can tell you how important a subset of feature is. And because it's a non-linear matter, so now we can really model the interaction effects between features. Okay? We also have this supply index and the action index, which can give you a very great insight of your model. For example, now we can answer the question that if the two features, do they complement each other, or if there is some redundancy between the two features? This kind of question now we can answer because we have a non-linear matter underlying the model. And of course, the model itself is monotone because Choquet integral is an integral. So integral by definition, it is monotone. So we have a monotone model here. Okay, 4 minutes. Now let's look about parameter estimation. We now have the model. Of course, we want to know how can we get the parameter from the data. We have the following parameters. So non-linear matter mu, utility threshold beta, and the position parameter gamma. I just want to mention that in the most general form, the matter can have a number of parameters which is exponential the number of attributes. Of course, it brings some computational challenges. But this is not the focus of the talk here. I will come back to this point in the end of the talk, in like 2 minutes. Then we use a micromolecular approach to get the parameters. And a very attention to details here is we represent this Choquet integral during the optimization using the so-called mobile transform. It's basically the same thing, but this kind of transformation can give you some mathematical convenience. Okay, so this is the optimization formulation. So if you're familiar with logistic regression, actually this objective is quite similar if you do mass molecular estimation for logistic regression. The only difference here is now the linear part is replaced by the Choquet integral. Okay? We have constraints on the threshold, we have constraints on the position, we also have constraints on normalization and monotonicity. And you can show that it is actually a convex problem. So some standard technique can solve the problem properly. Okay, so this might be a table. I try to summarize for you. There's a lot of numbers here. We have tests on 9 monotone binary classification dataset. We test 5 different methods. CR is our short regression model. And because CR is an extension of logistic regression, of course, we have to compare with logistic regression, LR. And we have 2 nonlinear classifiers. It's kernelized logistic regression with polynomial kernel and with Gaussian update kernel. So for polynomial kernel, we have degree of 2, so we can model the low-level interaction between features. And the Gaussian kernel, we can, of course, model much more complex interaction between features. We also have another nonlinear monotone classifier. It's called MORE. It is a rule-based classifier, which is represent the state of art in the monotone learning field. We have using different portion of data as training data. We have 20% using the training data, and more of the data used for training, 80%. Now, all the number you see here is a loss, and it's an average value based on 100-time repetition. So here, the average rank of each method on different settings is summarized in the end of the row. So there are several messages I want to send. But first of all, CR is in general very competitive, even compared with MORE. It's a very good performance. And also in general, we found out that on this data set, the monotone classifier is indeed then the one which is not monotone, because we have a monotone data set, it also makes sense. And very important if you compare choquistic regression and logistic regression. So if your data is limited, you don't have so many data, then you found out that actually in that case, logistic regression is even better. The rank is even better than choquistic regression. And at the same time, the choquistic regression suffer a little bit from this overfitting effect, because we indeed have a more complicated model. But when you have more and more data, choquistic regression has become consistently better than the logistic regression. Okay, I have talked about this interaction index and Choquet index. So I just show you a very short picture, which is the values of these 2 indexes. And this you can just compute based on the equation I showed you in the earlier slides. Only one thing I want to mention. So here is the Choquet index, which is somehow tell you how important one criteria is. And this is on the car evaluation data. I'm wrapping up. We found out that for the car evaluation data, the safety of a car is, of course, very important. It is here. At least it's more important than how comfortable the car is. But the safety is not as important as the price of the car. So if you really work in the car industry, you probably know this is actually true. Okay, so I wrap up. Here in this talk, we somehow the use of Choquet integral in machine learning, and especially in designing monotone nonlinear classifiers. As a concrete example, we propose this so-called choquistic regression model, which is the extension of logistic regression. I have shown you some very first experiment results, which is somewhat promising, and also encouraged us to further investigate other issues. I have talked about one small problem, it's about the complexity of the problem. Now we have some possible solutions, which is instead of to model a non-additive measure, which had the full capacity, we could also model a non-additive measure, which only have a limited complexity. And of course, the question is then how do you control the complexity in a very efficient way? And just one last thing I want to add is, we are currently investigate a theoretical aspect of this learning machine. That is, we want to investigate what is the weighted complexity thing related to this model. And we have a poster section. If you are interested in this topic, or if you're familiar with the weighted theory and learning theory, I would really like to talk with you about some other things. And if you don't have any question now, I'm back from as well. So. Thanks a lot.
We're running a little late, but I think we have a bit of time for questions.
It probably need some time to come up with question, but we were around. I'm around. Ali was also around. He's the co-author of the paper. So if you have any question, you can just jump to us and spend any time.
Have you ever posted in the?
Yeah, he did.
Given that there is the lunch break now, there is ample time for bilateral discussions now. So maybe we can use that as an opportunity to thank all speakers again. Thanks for being here. The program